Assalamualaikum warahmatullahi wabarakatuh. My name is Muhamad Mukhriz bin Mazlan. I'm here to present my final year project, Development of Multirotor Sentry Drone for the Malaysian Army. I am a semester 8 student from Faculty Mechanical Engineering of UiTM Shah. My supervisor is Dr. Rizal Effendi. In introduction towards my thesis is about the development of a surveillance drone that will be used for Malaysian armed forces, in which it is a joint venture between UiTM and ATM thought out by my supervisor, Dr. Riza Effendi, and it is also to create a drone-centric faction within FTTC labs to develop and research drone technology. Previously, Namtor, on my right, is a 6-rotor umbrella type drone that was thought of by my seniors to be used as the drone in this thesis. Due to the pandemic of COVID-19, I'm unable to go to the lab and such and unable to run research on this drone. Even so, Photor on my left is a 4-rotor FPV drone assembled by me at home and is a good substitute for Namtor in that the main purpose of surveillance is achieved. Photor will be the main drone for this thesis and will serve as a drone for this development. A problem statement: military bases are still using soldiers to run guard missions in their bases. This is a problem in that it requires too much time and too many soldiers just to run a few rounds of surveillance to find trespassers. This can be easily helped with the drones and easily used by the military. Another problem is that Malaysia's usage of drones, although are used nowadays, is not on par with United States or any other developed nations. My objectives for this thesis is to carry out the optical instrument installation of 4-Tor, to receive data from flight and to use that data to evaluate the mathematical model of Photor after installation of optical instrument. And lastly, to take images and evaluate the quality of it if it can be used for military use. The importance of this thesis is to provide valuable knowledge about the development of homemade UAVs or lab-made UAVs that are assembled and created in our own labs in our own countries. Nowadays, we see these drones that are in the market that are assembled in China or assembled in other countries and sold to us in a very high cost, and we can cut this cost significantly with this thesis as a valuable insight into its development of drones. Secondly, to enhance the relation between UiTM and the Malaysian military, and to improve the application of UAVs in military use. And lastly, to serve as a benchmark for future development of drone technology in UiTM, specifically FTCC labs and mechanical engineering. Now, for the theory of drones, drones are somewhat of a small aircraft in that it still uses the same basic principles of an aircraft, where there is a pitch, a roll, and a yaw. This is based upon the axis of it, the normal axis of X, Y, and Z, and it changes its roll, pitch, and yaw with the rotational speed of each of the propellers. So say if you want to make a roll, you just decrease the rotational speed of one side and it will roll to the left. This is going to be the basis of my mathematical model further on. The methodology of my research, the scope of my research is to just provide a development for a surveillance drone. In that case, I need to have an area of which I can fly and take some pictures. I'm using my own park nearby, in that I believe this is a suitable way for me to create a somewhat area of surveillance and safely run this project within my own household neighborhood and not go against COVID-19 protocol. So this is a video of me testing out the drone. As you can see, I am not a trained drone pilot, but I make do and I practice with the photo as much as I can. Even so, I've crashed this photo for about 6 times now, and I've replaced the battery twice. I've replaced the propellers 5 times, and I've had to buy from online shops some parts that I've broke, but I make do. So this would be a video of which I have improved greatly in my flying ability, in that I'm able to stabilize myself in a set altitude. Granted, this is not a DJI or a market-based drone, in that it's user friendly. No, it's a drone that when used, uh, is based upon the controller that I have used, in that the left stick is not altitude, it's thrust. So this is how I collect data from the photo. I use Betaflight. Betaflight is a massively used software for drone enthusiasts, people who are using it for FPV racing. It is a good way for me to get all the data I can from photo, in that it is a good way for me to evaluate the data later on. The most important part is black box, in which after you activate the mass storage device mode, it creates a black box in which you can visually see a graph of the behavior of the drone. Now this is what you get after you press that button. Black Box Explorer is a way for you to see it, and what it does is create a graphical viewing software, and a graphical viewing graph, in which you can clearly see the behavior of the drone based upon the gyro, accelerometer, RC rates, and so on. I can change these components in the legend, and I can view these things in a table, such as right now, in its units indefinitely. The most important parts are the gyro, the pitch, roll, and yaw, motor and accelerometer, and set points. This will be used, and once I export it into CSV, into an Excel file, it can be deciphered further on. So Raspberry Pi is the main optical instrument that is going to be used for the capturing of images and video. Raspberry Pi is a credit-sized computer that I'm using as a camera, and can be programmed to do many things, as I will show you later on. I'm using it to create object detection and human detection. So how I code in Raspberry Pi, I've already run all the settings of the Raspberry Pi, and I've connected it into my network, which is my home Wi-Fi network. And from this application, the VNC viewer, I'm able to access the Raspberry Pi remotely without having to connect it to my laptop. So this is the terminal. I do all my coding in this, and this is the TensorFlow one, which is the program that is being used for object detection. Later on, I'll show you some tests that I've run. So these are the tests. So as you can see, the Raspberry Pi detects the object in the video on the left, and my brother, the human, and it shows the percentage of accuracy. So this Raspberry Pi can be programmed to do many other things, such as get the information of weather and so on. So the result is what you can see right now is the final configuration. I've just strapped the Raspberry Pi and a battery to the photo, but it flies just the same. So this is the flying data that I've chosen. I've called it Flight Alpha because it's the easiest way to show that I have flown the drone onto one set altitude, stabilize it for a bit, and then land. As you can see from the center part of the graph, there's a little bit of disturbance. That's due to the me trying to stabilize myself in a windy situation. In the black box, it doesn't show you the altitude because the photo is not does not have a barometer or a altimeter in which I can clearly get the altitude. So the mathematical model, I start with the weights of all the components, realistically speaking. So the table on my left shows you the weight of the components, the quadcopter itself, the Raspberry Pi, the first LiPo battery for the quadcopter, the second LiPo battery for the Raspberry Pi. So the total is 712. So from the motor itself, we can decipher the RPM, which is 8,500 RPM for one rotor. And so for the force of one rotor, for one motor, and we put it into the formula, which is Wi squared K, which is equals to half of the mass of the whole package times with the gravity, and you get the force of one motor creating 1.056 newtons to overcome the drag of the weight. So B, which is the change of altitude and the change of pitch, your rule is equal to 0. So the torque of the motor is I omega dot I. So the amount of thrust required to overcome everything is in the overall formula, which is T minus W, which is the weight, equals to mass acceleration Y. Since I am in level flight, which is just not moving at all, but there's a difference in altitude, the thrust required is 6.98 newtons. So going on, I as I told you before this, I is required for this formula. Since I'm able to calculate I effectively myself, because this is a very complicated machinery, I use OpenVSP to create a silhouette of the photor, in which the main aspects of it, which are the legs, the main body, and the propellers, I get the silhouette of photor. And by using OpenVSP, I'm able to get the I value of everything, which is the mass moment inertia. So in the above equations, you can see the traditional axis X, Y, and Z based on thrust. N is the Euler angles that I've mentioned before, gamma, theta, phi. Force equals to the amount of velocity that you give. The refresh time of each cycle in the drone is 20 milliseconds. So A and B are the main formulas to mathematically describe what is the behavior of the drone, and this is the formula that I use to get the values. So as you can see, it is in a matrix form because drones operate in a 3D space. So it is necessary for you to put it in a matrix form because it operates in 3D space. So R, I just input the values from the formulas below, and I from the values that I get from OpenVSP. Uh, so the torque required for one motor is 11,0376305 newtons meter squared, and the cm is 15813224.21 meter negative squared. So these are all the formulas that I've used. This is the formula that describes the motion of photon in traditional sense: x triple dot, y triple dot, z triple dot. The torque, the overall torque in 3D space, which is that matrix times with the thrust, and the velocity, and sorry, acceleration of each of the rotor gets from the accelerometer in the black box. So in conclusion, this is the formula of the mathematical model of photon, in that the mass moment inertia times with the omega dot equals to the following, and the mass times with the traditional axial axis double dot gets so on. Note that the some values I have not put in because it is for the mathematical model, in which if you want to put in the values in a specific given time, you must calculate the speed of the photon at that specific time. So these are the flight pictures. These are pictures that I've taken in the during flight, and as you can see, photo detects cars, humans, and and is able to decide and is able to differentiate between humans and cars and so on. Thank you so much for listening. For Q&A sessions, my personal contact is in the slide right now, and the email also is on there. Thank you so much for listening.